the surface must be leveled or planarized. This creates the flat surface required to produce precisely detailed patterns. The next mask defines the openings through which the metal wiring will be able to contact the transistors. By etching the unmasked portions, contact holes are created. Through the microscope, we can see these holes as small dots. A combination of tungsten and aluminum are then deposited onto the wafer. The next mask patterns the aluminum into microscopic wires. These narrow metal strips extend from one transistor to another and form the first layer of wires connecting the circuitry. In sophisticated circuits, the wiring is so complex that it's impossible to complete with a single layer. This highly magnified photograph shows a device with 2 layers of wiring. This cross-section shows 5 layers. Each additional layer typically requires at least 2 additional masks. After all the desired levels are in place, a final layer of insulation is deposited to protect the fragile aluminum wiring. In the last photolithography step, small pads along the edge of the microchip are left exposed. These white aluminum pads are the contact points between the microscopic wiring of the integrated circuit and the outside world. The wafers are then stripped of photoresist, and the run is complete. Despite the care taken in the fabrication process, not all the chips on the wafer work. Now the individual chips on the wafer are tested. Here we see wire probes touch each of the small pads to make sure electricity is flowing through the circuit. This inking machine marks each failed circuit with a black dot. Soon the wafer will be cut into individual chips. A sticky blue mylar tape has been placed on the back of the wafer so the chips stay in place while they are cut. In soapy streams of water, a diamond saw cuts through the silicon wafer without cutting the tape beneath. The chips on the wafer are separated, but they stay attached to the tape. A camera scans the individual chips. The electronic eye detects the ink blots that mark the failed chips and skips them. The good chips are removed. The tiny fragile chips need a protective frame. These metal strips will be their protective housing. Here we see the small integrated circuits being glued to the metal strips. A gentle scrubbing motion ensures a good contact. This high-temperature oven hardens the glue. Now the metal frame must be connected to the small aluminum pads on the integrated circuit. In slow motion, we see the thin gold wire connect from the pad to an individual pin on the frame. These pins are now attached to the microscopic circuitry of the integrated circuit. To further protect the chips and their fragile wire bonds, the devices are encased in hard plastic. After several minutes, the encapsulation process is complete. The chips will eventually be soldered to a printed circuit board. In order for them to attach properly, the pins must be thoroughly cleaned and then plated. Next, the strips are cut and the tiny pins are bent so they will sit properly on the printed circuit board. Quality control is very important. Before the chips go any farther, they are tested. They are loaded onto test boards which will be placed in ovens. On these boards, the chips will be electrically stressed far beyond normal conditions. Weak chips are forced to fail before they're put into a customer's product. In rows and rows of test ovens, the chips are powered up and exposed to high temperatures for several hours. In another test, the chips are exposed to contrasting cold and hot temperatures. An electrical socket then tests each pin. The chips are sorted according to those that meet the highest requirements, those that meet lower requirements, and those that have failed. We mark the chips that pass with the manufacturer's logo. They are visually inspected, laser marked, and packaged for distribution. The printed circuit board allows many chips to communicate with one another and with the outside world. Signals travel between chips along electrical pathways on the circuit board. The maze of electronic pathways is created by circuit board designers who find the most efficient way for the signals to travel. These designs are transferred onto the bare printed circuit boards. Let's follow the assembly line and see how a complete system, such as a computer, is actually made. Much like screen printing, solder in the form of paste is pressed onto the board through a brass stencil in the areas where microchips will be attached. Each microchip is automatically positioned where the solder paste was deposited. Now the boards go through an infrared oven. The solder melts and bonds the microchips to the top side of the board. Tiny chips are temporarily glued to the bottom of the board until they can be soldered later in the process. The other way of placing parts on the board is the through-hole assembly process. Here, electronic components with straight pins are inserted through holes in the circuit board. The wires are then clinched from underneath to hold them in place until they are soldered. This eyelet setter, or rivet press, secures any large connectors located at the edge of the board which need extra strength. The circuit board now contains all of its components. An operator makes a final visual check. A wave solder machine does the final soldering. The bottom of the board is first coated with solder flux. This substance prepares the pins so the solder will adhere correctly. From beneath, we see the hot solder just touches the small wire pins. Next, we test the boards and send the good ones to system assembly. We place the boards in a computer casing. The speaker assembly and the data cables for the disk drive are attached. The disk drive mounting bracket with the floppy drive is inserted. The hard drive snaps into place and the drive power and data cables are connected. The power supply for the computer is installed. The system is fired up to prepare it for the first phase of testing. Additional temporary memory and test cards allow software to exercise all areas of the system. We monitor the testing and verify that the system is running correctly. The test cards are removed, and the assembly of a personal computer is complete. And me? I'm ready for my own kind of run.